Did you hear it ding? I don't know why I did that though. All right, here we are. Friday. Monkey problem. Let's see if you all got A right. I'll bet you did. You are to draw the free body diagram on the monkey showing all the forces and label them, of course. So did you draw one straight down? What is that? mg. That's the weight of the monkey. Did you draw one that like this in that direction? That is tension in vine B. Did you draw one in this direction? Which one should be longer, or should they be the same length? Tension in B or tension in A? Which one's greater, do you think? B should be greater, it's more vertical. Anyway, so if you're drawing them with some appropriate length, the A would be a little bit shorter than the B. Okay, let's look at the rubrics and see how they wanted to grade it though. For part A, worth 2 points. For any one correct and labeled vector, you got 1 point if you just have one that's correct. The second point for the other two correct, you have to have all three for the second point. And if you have any extras, then you lost points for that. Okay, so they did have to be, they did not mention in the rubrics the length, therefore, at least on this exam when it was given, they did not worry about how long they were. You just had to have them in the correct directions and labeled correctly. All right, 2 points. B, determine the tension in vine B. What is the tension you have for vine B? I think I'm going to call on Claire.
I worked on this one for a long time. I can't figure it out.
But you don't have an answer? Okay.
I got one.
Lucy, what's your answer?
I got 42.3.
42 newtons? Anybody else get 42 newtons? Jack did, and Tony did. 42 is correct.
Let's do
FaceTimed
it.
Jack
Let's
last night.
go
She
over
helped.
it.
I tried.
All right, there you
It's in my
go.
notes, but I don't know how to solve it.
I saw it in the next one.
You got here, this is worth 4 points. You got 1 point for any indication in your answer that the sum of the forces is 0. If you wrote that and then followed up on that, or if you wrote something that shows I'm letting the forces add up to 0, you got the first point. The second point was for trying to put the tension vectors into components. There's a tension X, and here's the tension for vine B, Y. And my blue marker's not doing very well, so I'll go back to some other color. I'll go back to the black one. Here's the tension in A, X, and here's the tension in A, Y. If you, now, it told you in the question, don't go back to part A and draw components there, but you could draw another one, and I would have drawn another set of vectors where I can look at the components. Okay, so if you drew the components or you used the components, they could see in the math you use cosine or sine, then you got the second point. The third point was for attempting then to use that to solve the equation. So if you look at the y components, what you have is the tension y plus the other tension y, and one of these is A and the other is B. But if you add up the two y tensions, that's got to equal the down mg, doesn't it? The ups have to equal the down, that way they add up to 0. Okay, so from there, you know that the AY is the sine of 30, because it is, the y component is opposite the angle you know, and we know theta is 30. And for B, it's tension B times the sine of 60. Okay, and that's got to equal mg. Do we know the mass of the monkey? 5 kilograms. So we know mg. It's 5 times 9.8, which is not really 50, but it's 49. Yeah, it really is 49, isn't it? Okay, So if you started out this way, or if you wrote that or that, you've got the third point because you're trying to solve the problem using the components. Here, of course, the question is tension in B. You don't have anything else to work with that. I mean, you're going to have two unknowns, and so what you're going to have to do is go to the X components and say the sum of all the X forces is also 0. And the X forces would be, well, the BX, which is cosine 60, has to equal the AX, which is cosine 30. And from there, what I would do is take probably solve it for FTA, and that would be FTB times, well, if you do it the other way, anyway, cosine, I won't finish the math, over cosine, one of these is 30, one of these is 60. That one's 30, here you go. B was 60 and that was 30. If you, just divide that out and you get a number for FTB and that's equal to FTA. And the reason I did that is now I can plug that into FTA and I'll have an equation with only one unknown and it's FTB. Okay, so without finishing that out, that's how I would have done it, but you've got two equations with two unknowns. Once you get this far, you've got two equations with the same two unknowns, you just need to solve it for FTB. All right? Now, that should come out to be 42 newtons. If you plug that thing in here and then solve it for FTB, 42 newtons. Okay. C. Question C is the monkey releases vine A and then swings on vine B. So the monkey is now going to swing this way because he let go of, now it's just vine B that he's holding on to, and so he's going to swing down like that. And the question is determine the speed here as the monkey passes through the lowest point. All right, you have an answer for that. I think I'm going to call on Nate. What do you have for part C? Let me look it up myself. What do you get? 5.1 meters per second. Let's see what the right answer is. It's 5.1 meters per second. Anybody else get that? Okay, good. A lot of you got that. This is just energy conservation. U up there equals K down here. Did everybody do it that way? mgh equals 1/2 mv squared, and you had to figure out what h is, that height, that h right there. Okay. All right, I'm going to move on so we don't spend too much time here. Most of you got that. Part D is determine the tension in vine B when it's right here. Now we want to know the tension in vine B when it's here. It's not going to be the same as it was there. So, do you have an answer to part D, Tony?
I have 61.75 Newton.
Anybody else get 62 newtons? You round it off? That's correct.
I got 65.
It should round off to 62. Here, when the monkey is right there, at the lowest point here, when the monkey's right here, free body diagram, that's mg, and that's the tension that we're looking for. That's the question. What you know is that the sum of those forces is equal to ma, but the A is centripetal. It's moving in a circular motion right there. And so the sum of the forces is tension minus mg. The tension is up, the mg is down. So tension minus mg, and the ma is mv squared over r. The acceleration is v squared over r. And you just found v, that's your answer in the previous part, which is supposed to be 5.1. You know the mass of the monkey, and you know r, that's the length of do we know the length of the vine? Mm-hmm. Okay, yeah, we know that too. So you know all of that, and you also know mg. You can solve that for tension right there. So the tension we're looking for would be mv squared over r plus mg. Basically, just plug in numbers you know to that and solve it. And that's supposed to come out to be something close to 62. All right. Does everybody understand the things you did? This was a good problem because it made you first look at components. You're going to have to be able to do that, get components of forces, and deal with the y forces add up to 0 and the x forces add up to 0. Because the monkey wasn't moving, no acceleration at that point. Then it made you think about conservation of energy. You know that's going to be on the test. U equals k in this case. And then finally it made you think about circular motion, centripetal acceleration. So that had a lot in it. Any questions about that problem? Anybody? All right, then get back out the multiple choice questions you were looking at yesterday. Let's go back to that. I gave you all the answers. You may not have finished in class, that's all right. And we kind of talked about at least the first page. So turn back to the back, the second page. And look at those answers and tell me if there are any of those you want to talk about. You're not sure how to do it. Any you want to discuss on the back page there?
1, then 6,
Number 6.
and 7, and 8. Also 9 and 10.
Okay.
Actually,
Well, let's start with 6 and then we'll see. Person A throws a stone of mass m with initial velocity VO at an angle theta with the horizontal from a bridge that is h meters above the water level. So I've got a picture there. You're that high above the water, and person A throws it with initial velocity VO. B throws a stone of mass 2m with the same initial velocity in the horizontal direction. All right, so person A is throwing it like that, VO, where that's theta, and that's person A does that. Person B throws it this way with a speed VO also, but it's twice the mass. That's 2m, and this one was m, and that's horizontal. Okay, the question is which of the following is correct for the speeds of the stone when they strike the water. So this one is going to do that, this one's going to go up and then do that. And then they're both going to land in water at different places. But the question is, how fast are they going when they hit the water? Okay, the right answer is D, which says they're going the same speed. Who can tell me why? How do you know that? It looks like the one that went farther, maybe it went higher. Shouldn't it be going faster when it gets down here? But no, they land at the same speed. Anybody have an answer to why that's true?
Fired.
You about to what?
They were fired at the same speed.
Right?
You don't lose speed. I mean, you do, but you gain it back with gravity.
That is what happens. How in physics can we justify that, though? What physics principle comes to mind? It's what?
Free fall.
Free fall is involved, and the free fall is the same. The acceleration due to free fall is. But think about energy. Were you about to say something about energy, Erica?
To myself, because it might be wrong.
She was saying conservation due to energy.
What kind of energy does each stone have right here once it starts to move? It has U, which is the same for both initially, right? And it has K, which is not the same. Well, it's not the same for both because one has twice the mass.
Yeah. Okay.
But the V is the same. Okay. What was the? Oh, the times are not the same. We'll talk about times in a minute. Okay, K plus U. The U's are not the same either because it has twice the mass. That one does. Okay. at the end, they have nothing but K, right? But this one still has twice the mass, and so the m's are going to cancel out anyway. When you set them up equal to this, equal to that, there's an m in there, and one stone has two m's here, but it also has two m's there, so the two m's are going to cancel out. This one has m's here, but it also has m here, so the m's are going to cancel out. So the mass ends up making no difference. That's what you have to see. Because the only difference was the mass. The V's are the same. The things that don't cancel out, the V and the H, they don't cancel out, but that's the same for both. So they start out with the same, once the M's cancel out, they start out with the same here, so they've got to end up with the same. Okay. I don't know if that makes sense to you, but it's true. You couldn't, if you had to justify that, you couldn't say they have exactly the same energy at the top, because the one with 2m has more energy because it's 2m. However, when you're comparing that energy to that energy, that's when the m's cancel out of the equation. You've got 1/2 2m times v squared plus 2m gh has got to equal 1/2 2m v squared. See, the point is the 2m's go away when you set up the equation. That's what I was saying. So the fact that one has twice the mass makes no difference. It canceled out of the equation anyway. All right, that's number 6. Oh, the times. Why does this one take more time? You can guess that without having to do much math. It's going to go a lot farther. It just takes more time because free fall is the same, acceleration is the same. So if it goes farther, it's got to take more time. You can just reason that through. All right, so the time is greater for that one. All right, do we need to do number 7?
Yes.
All right, look at number 7. I have a 4 kilogram block up here, and I have a 2 kilogram block here, and this is on a table. And what is the loss of mechanical energy? All right, it says it's rough, so there is friction. So see, there's tension that way, there's friction this way. All right, so there is friction. What's the loss of mechanical energy? That loss is due to friction. Okay, that's why the loss is there. What you need to do is calculate the total energy before, and then the total energy after, and then subtract. See how much was lost. And the total energy before, potential energy, this thing is gonna fall some distance, so it has a U before, mgh, and that m is 2. This one doesn't change. It's going to move the same distance horizontally, but it doesn't change potential energy. So we can ignore the potential energy of this one because it's not going to change. Whatever it is in the beginning, it's going to slide to the right, but it'll still be the same at the end. So just ignore the potential energy of this one. That one, though, really is going to change potential energy. Now, the K, this one starts at 0, and so does that one. So initially, that's the total energy of the whole system initially. Nothing's moving yet, and that one doesn't have any U that matters, and so that's the initial. And if you multiply 2 times 10 times 3, you get 60. I use 10 for G just to make the math easy. So that's before. After this one has fallen, so it has no U at all, but it has K. Right? This one also has K because it's moving after the whole thing has moved a certain distance. So that's the total energy after, and if you add those up, you get 1/2. They're moving the same speed, so I'm going to say 1/2 6 is m, 2 plus 4. Instead of doing K plus K, I'm just putting them together. And that v squared was, you were told, was 2. 1/2 mv squared. They're both moving at 2 meters per second. You were told that in the problem. So that's the energy after. And if you calculate that, you get 12. So the answer is just 60 minus 12. All right, you see what we did? Everybody? That's how much energy was lost. Apparently due to friction. Okay, number 8. Do we need to do number 8? Oh, it's still about the same thing. The coefficient of kinetic friction between the 4 kilogram block and the horizontal surface. They're asking you about mu. And so what you now know is that work done by friction is the force of friction times the displacement, right? Work done by anything is force times displacement. The force of friction is mu times the normal force, and the normal force is equal to mg because there's mg and there's normal force. Those have to add up to 0. The block is not accelerating vertically, so that's how you know normal force is the same as mg. And so that's what you've got there. And you already found the work to be 48. So this is one where if you miss number 7, you're going to miss number 8 as well. Because you wouldn't have a 48 right there. But if you do have a 48 right there, you know m and g. The m is 4. See, there's no friction with the 2. The friction is between the 4 and the surface. So the m is only 4, because that's where the friction is. M is 4, G is 9.8, and delta X is 3, or I think it was 3. That's the distance it slides. So you just solve that for mu, and that should come out to be 0.4 if you do that. Again, you had to have the 48 from the previous question, right? Or else you're going to miss this one. You wouldn't come up with the right thing. Okay, that's number 8. Everybody all right with that, with 7 and 8? All right, then number 9 is asking if the angular velocity omega and the radius r are both doubled, the tension in the string would be. What you know is the tension, because it's moving in a circle, the tension is equal to centripetal force, which is, it's mv squared over r, but it's also, you learned in the last chapter, m, and you learned that vt is r omega, didn't you? No, r omega squared, that's what you learned, wasn't it? So, no, I did that wrong. That's A. There you go. Is that right? A. Centripetal acceleration is r omega squared. No, that's not right either. What am I trying to remember here?
I don't know. So confused. Why can't you just do mg squared over r?
Centripetal force, of course, is ma. Centripetal acceleration, that was r omega squared, wasn't it? Was it really? Okay. I was just trying to remember my equations and I was messing that up. All right, so that was just in the last chapter, we learned that. So ma. And the reason we chose that equation rather than v squared over r, which of course it is, we can't use v squared over r here. We don't have that information. And because they're asking you about omega and they're asking you about r. If you use the v squared over r, you don't have omega in there. This way you do, you can just look at them. Well, what happens if we double, if the tension is doubled, that's this, on the left side of the equation, that number is doubled. And the tension in the string is just TO, sorry. If the angular velocity omega is doubled and r is doubled, what happens to the tension? That's the question. All right, so if you double this, that's 2 times the r. If you double this, that's 2 squared, that's times 4. So what happens over here is this side of the equation increases by 8. That has to be 8 times as much. Okay, that took me a long time to get through that, but that's the right answer. That's the way to think about it.
What is
The right answer is 8 TO.
how is mass involved?
F equals MA. This is A.
Oh,
And yeah, centripetal force is M centripetal acceleration. So it's M, and that's centripetal acceleration. Okay, that was number 9. Number 10, a mass is released from rest at its lowest position. What's the tension in the string? This is where it starts here and it swings down like this. And this is kind of like the monkey problem again. Here, what you say though is we can't really solve this with energy methods, because the question is what's the tension, and so you've got to deal with it this way, where that's tension and that's mg, and those two things, tension minus mg because it's down, have to equal mv squared over r. So the tricky thing in number 10 is you don't know v, you've got to figure the v out using energy methods. So you do have to use u up here equals k down here just to get the v. So you can, this is a v right here, it's just so you can plug something into v. And so what I did was, for energy methods, I said the u is mg h, which in this case is r. R is the height, because that's the length of the string. And the k is 1/2 mv squared, and v is what I need. So if I solve that for v squared, and I'm just going to solve it for v squared, it's 2gr. Or v would be the square root of 2gr if you wanted to solve it for v. But I'm solving it for v squared because look, that's what I'm looking for over here is v squared. All right, so tension minus mg, tension would be mv squared, but we just said v squared is 2gr. 2gr, that's v squared, over r, and so the r's are going to cancel, and you get 2mg. You get 2mg, wait, I didn't finish the equation. Okay, plus mg, there's the whole equation. Tension would be mv squared over r plus mg when you bring it over here. So this becomes 2mg, and that's mg, then the answer is 3mg. 2 plus 1. There you go.
Okay.
Now that was more work than most multiple choice questions require. You had to do 2 pretty big things just to get one answer. So I think you're not very likely to see all of that in one multiple choice question, but all of this is physics you should know how to do. Yes.
Did you point that over there so I could see it?
Oh, Lily, you don't know what I was doing over there, do you?
Good idea.
Wait, seven.
I wasn't
All
even
right.
thinking of that.
Any other questions on this multiple choice assignment from yesterday? Anybody? Claire, what are you doing?
I'm trying to get in it.
She can't see you, Claire.
Is it in it? Is it
All right,
there?
we are going to,
Something there again.
I'm just going to go back and start talking about situations unless somebody has a question about a specific thing. Anybody have a question for our last 15 minutes of class? Anybody? Or you want me just to go? Anybody have a question? A topic you're most worried about?
Pendulums.
Wait, can we just start going through everything again? Like we were last time we were in class?
Like start at chapter 2.
We already did.
Let's
We got
just
there.
stay here all
We
day and
already-
not go
we
to
already
any of our
did.
other
Well, that's what I was
classes.
going to do is pick up with where we stopped.
Just keep doing that.
Just
please.
going through
Yeah,
things.
Let's go.
We did projectile motion, free fall, we did graphs, we did
We were on a triangle.
We did elevators.
Inclined plane was the last thing we did.
Inclined plane is the last thing we did. Okay. Then let's review momentum.
Oh, yeah.
Here is
P.
an object going that way, and here is an object going this way, and they collide. In the collision, what is conserved? A, momentum, B, mechanical energy, C, I don't know what other wrong choices would be, but A or B?
What are the questions?
What's conserved when they collide?
I know, but what were they answered? Like what?
Momentum or mechanical energy? Or both? Or neither?
No, mechanical.
I don't know, but my eyes twitching.
Momentum is conserved, mechanical energy is not. Because some of the energy, initially they both have kinetic energy, don't they? After they collide, there'll be less kinetic energy because some of that energy turned into other things like what?
Heat.
Heat, sound, some energy just to dent the wall of the car. So all those things take energy away, so after they collide, they'll have less kinetic energy. But momentum is always conserved in any collision. You have to remember momentum. It's not a theoretical thing, it really is conserved. So what you know is mv plus mv has to equal mv plus mv, where this is before the collision and this is after the collision. Momentum is mv. All right, so before the collision, let's say that has a mass of 1 and that has a mass of 2. It's bigger. And this is going a speed of v, and that's going a speed of 2v. How about that? All right, that's this. Let's just use letters. That's m, and this is 2m. That's 1m. That's 2m. 2v. 1v, and they collide. Who's going to win? The 2m is going to win, isn't it? Mm-hmm. All right. So initially, before I've got the mass of this is m, and the velocity of this is v. What about that one? The mass is 2m, and its velocity is 2v. What's true about the sign, though? Am I going to put a plus here? That one's positive because it's moving to the right. This one's negative, moving to the left. You need to remember that momentum is vector. So the direction matters. So yeah, that's got to be a negative over here. That's the initial momentum of the system. What does that come out to be? Add the total on the left of the equation. What do you get? What's 2 times 2? That's 4 mv. What's 1 mv? What's mv minus 4 mv? Negative 3 mv. Is everybody with me on that? You can all take 1 minus 4. Okay. On the right side is what's going to happen. And let's say when they collide, you're told in the question that they stick together. Okay. They're going to stick together. That means you can factor out the v because the v's over here are the same. So now I've got m plus 2m. That's the total mass, m plus 2m, and those two v's over here, which is the question, they're the same. So I can just put it there. What's the answer? I've got negative 3 mv is equal to 2 plus 1. 3mv. Did I do that right? What cancels out? By the way, this would probably be called VO or something, so you can tell that's the question. This is the thing that can be in the answer. And yeah, the m's cancel, and the answer becomes VO. Is that right? Negative VO, right? So it would be moving to the left. The whole thing stuck together would be moving to the left with the speed of VO. All right. Just reminding you how conservation of momentum works. Everybody get that?
Why can you combine the 2m? Like, why does it become 4mv? Why is it not 2m, 2v?
Over here?
No, up.
Up here?
Yes.
It is 2m, 2v. 2 times 2 is 4mv.
But it's not the same.
2 times 2 is 4. M times v is mv.
No, like they're together already.
Like,
You're just
really,
like
they just look
rearranging it.
separated because they have parentheses. But if they didn't have
Yeah.
parentheses, it would be the same. It would
I just
all
drew
be
the
together.
parentheses to show that's the mass of that thing and that's the velocity of that thing, but when you
And it's
multiply
all
them together,
multiplied together.
2x times 2y.
So like whatever numbers are there, you can multiply.
okay. Momentum. Next. Next. Gravity is kind of a small thing, but we haven't actually mentioned it anywhere else. Do you remember this equation? Did you learn that equation at some point?
What about
Force of gravity between any two objects can be calculated that way, where that's the mass of one object and that's the mass of the second object. And that's R is the distance between them. So these could be two things like the Earth and the Moon, or it could be two things like two students in the room. R is how far apart they are, M's are the masses, G is the constant, which is on the constant page of your equation sheet. If you need that, you can look it up. So I'm not going to work a problem with that, I'm just reminding you, you know that. If you need to know the force of gravity.
Wait, isn't it like 6.11 times or something?
Something like
No,
that.
it's like 6.
6.6.
10 to the negative 11th, I think.
Yeah, okay.
Okay.
That's great.
Did we talk about, here, let's talk some more about circles.
Yeah.
I'm over there where Lily can't see again. All right, let's talk about circles. Did we review centripetal
No.
stuff the other day or not?
Not really.
Let's just go over this again. Here's a string with a stopper on it moving in a counterclockwise circle. Draw a free body diagram on it when it's at that spot for that instant. There's mg and there's tension. That's it. Is there a centripetal acceleration?
Yes.
Yes. And that would be calculated how?
RW squared or V
You can
squared
either do it
over
R omega squared, or you can do it V, and the V is the tangential velocity squared over R. Either, depending on what you know. Okay. That's centripetal acceleration. Even if it's moving at a constant speed, if it's moving at a constant speed, then you have a number for omega, or you have a number for VT. It's not changing. If it's moving at a constant speed. So you can calculate it. All right. If it is changing, you just need to know what is it right at that instant. What is the VT right at that instant? And then divide that by R, and you still got AC when it's right there. When it's up here at the top, now the free body diagram looks like this, doesn't it? mg is down, but now so is tension. Tension is always toward the center. So now, F, here, I didn't finish the forces over. If you're asked for the tension, go back to this one, I meant to do that. If you're asked what is the tension, well, the tension is equal to M times that, or that. Okay, either one of those. It's M times R omega squared, or it's M times V squared over R. Because that's the only force pointing toward the center. So that would be true. Up here you have two forces pointing toward the center, so you would have to say mg plus tension is equal to mv squared over R, or again, m r omega squared. All right, but it's both of them pointing in the same direction, so you add them, mg plus tension. Both of those are combining to turn the thing at that instant, because they're both toward the center. So they both make up centripetal force. When it's back over here, once again, you've got mg down, that's perpendicular to the tension, so the mg has nothing to do, has no component that's toward the center. So once again, the tension is the only thing that is making it turn, just like it was over there. It's the only thing that's toward the center. When it's down here, the free body diagram is mg down, but tension up. And so now, both of those are parallel with the radius of the circle, so you're going to say tension minus mg That's equal to mb squared over r, or again, m r omega squared. But here, they're in opposite directions and tension's greater because it's going to win, it's going to pull it up. So tension minus mg. Tension's up, mg's down. Okay, so all of that's true for centripetal acceleration of this little mass on the string. Okay. Then the angular quantities you just had a test over, and so don't forget that you know all of that too. There's some of that right there. But remember, omega and alpha are angular quantities. They would apply to every point, the mass, but every point on the string as well is moving at the same omega, the same angular velocity. If it's speeding up or slowing down, it all has the same alpha, angular acceleration. If it's speeding up, then it would have an acceleration that's tangential, speeding up or slowing down. So the v, t, and the at, those are not angular. They depend on the radius. How far out from the center are you? Those things do. These things don't. Okay. That was your most recent test, so you probably remember that fairly well. Remember, you've got a version of the big four that applies to angular. So you need to know the big four both ways. Okay, we have about 3 minutes. What question do you want to ask anybody?
Pendulums. The pendulums.
Pendulum, is that what you said, Erica?
That is
I'm
what I
sorry.
said. That's okay.
Pendulum, yes. Let's do that because I've heard that question more than once today. You hang this down and you pull it back and you let go and it swings back and forth like this. It actually has a period, the time to go back and forth, but we haven't really talked much about that yet. That's coming up in January. The thing you do know about it is that you can use energy methods where up here it has U and down here it has K. That's really all we've done with the pendulum so far. And so when you work problems where you had to find out this H, and you can do that if you know the angle up there, theta, because that's a big right triangle there, and that's the length of the string, and so is that. So you can, if you find H, then you have MGH, and then down here it has 1/2 MB squared. That's really all we've done with the pendulum so far this semester.
Find H for something.
Wait, is
How do you
that
find H?
Yeah.
wait,
Because
is
they
that
still don't really
H?
understand.
You use like the triangle.
That's that H over there, right?
This is the height when it's at that point.
Right, but like that's on that.
Over here?
No, like
What?
on the block when it's like all the way down.
It's a rectangle, yes, it's equal.
This is this right here is a rectangle.
Right, so that side has equal.
that
to,
H is the same as
is
this
that
H.
H right there? That's what
Yeah.
we're trying to find.
So it's
You're
Okay.
trying to find that.
So if like the length of the rope is 10, it's 10.
But when it's
So if you know the length of the string, you can, and you know that angle, you could find this leg right here. We'll call it Y, just so we call it something.
So
And then you can get H by, this is the total length of the string, subtract Y, and you got H. That make sense? Use your trigonometry using that hypotenuse and that angle to get Y, and then subtract Y from the total length and you got H. That's how you get H, or the U up here.
can you write that down?
Can I write that down?
Yeah.
Erica wants me to write it down, whereas I could just send her this video.
Oh yeah, do that, please.
Yeah. You
So
do
this is the
that.
link.
Or do both.
Do you want a link? Who wants a link to today's video? You
Lucy.
do? Okay. I'll just send it to the whole class, and if you don't want it, just ignore it.
Okay, that sounds great.
Sometime this afternoon, it'll take me that long before I have free time to actually upload it to YouTube. That's what I do. And then I'll send you the link.
Well, that's like,
All right.
this is the first time that I've studied.
Bell's ringing. Bye.
Yeah.
Bye.
Like, I want to get it done.
Wait, I want to be in it.
Anybody else want to say bye?
Bye.
I don't want to do it.
Oh look, this one comes back.
This is gonna be.
Minho, wait, bye.
You're all gonna
Wait,
be
why
on,
are you covered him?
you're all gonna be on YouTube.
Sorry.
Say bye.
Minho, say goodbye. Tell Lily.
Goodbye.
And Sophia. Oh.
The not sack.
All right. Hey, Kyle wants to say goodbye.
Kyle!
That was great.
That's so mean.
That's not mean. That's just Kyle. Look at it. Okay.
That really is.
That's how Kyle says goodbye. He's mean.